Hi, welcome. Today we're going to be talking about 5.1, the natural logarithm and differentiation. I know you've seen natural logarithms back when we covered pre-calculus, either with me or someone else you had pre-calculus. And today we're going to talk about differentiation when it comes to the natural logarithm. Okay, so recall the general power rule that said the integral of x to the n dx would be x to the n plus 1 over n plus 1 plus c. But it gave us the restriction as long as n is not negative 1. So if we have a negative 1 as our power, we couldn't do that. So what can we do? Why is that the case? There's probably a better way to express this. The definition of the natural logarithmic function. The natural logarithmic function is defined by, this is one of the definitions for it. Natural log of x is the integral from 1 over x of 1 over t dt, as long as x is positive. That is the definition of natural log of x. The domain of the natural logarithmic function is a set of all positive real numbers. You can only plug positive things into the natural log function. So these are going to be, that's why it's positive here. So if x is bigger than 1, you have the integral from 1 to x of 1 over t dt. If x is less than 1, you have, that's positive. You have the integral from 1 over x of 1 over t dt, and that's going to be negative. So the natural logarithmic function is an antiderivative of the equation dy dx equals 1 over x. So its antiderivative is the natural log. And that's why we couldn't discuss that case before. Okay, theorem 5.1, properties of the natural logarithmic function. The natural logarithmic function has the following properties. The domain is 0 to infinity, not inclusive of the 0, by the way. And the range is negative infinity to infinity. The function is continuous, increasing in 1 to 1. And the graph is always concave upward, or downward. It's kind of going like that. Theorem 5.2. Logarithmic properties. This is a typo here, so bear with me. Natural log of 1 is 0. Natural log of AB is natural log of A plus natural log of B. Natural log of A to the n power, that should be a power, is n times natural log of A. And natural log of A over B is natural log of A minus natural log of B. I'm sure you remember those. From your pre-calculus days. So let's use a graphing utility to evaluate the logarithm by A, using the natural logarithmic key, and B, using the integration capabilities to evaluate the integral from 1 to x of 1 over t dt. So we're going to do natural log of 0.6. So just plug this in the calculator, you get negative 0.510826. But if you use your calculator for this, let's see if I can get this Elmo going, see if it shows up okay. Yeah. I do have my calculator with me, yay. So this is how we're going to do the integration. This is how you do any integration with a TI-89 graphing calculator. Okay, so there's our calculator. Turn it on. That shows up a little better now. Now, F3, it gives you the calculus tool. So I'm going to hit F3. And the second option is to integrate. So we're going to integrate. What are we going to integrate? 1 divided by x. Then we do comma, so it knows the value, or the variable, comma x, x the variable with respect to which it's integrating, comma, and then it wants us to go from what to what. We're going to go to 0.6, so we go 1 comma 0.6. And what do we get? Negative 0.5108. The same thing as if I hit second natural log of 0.6. These numbers are the same. So that's how the natural log function is defined, and until you've had calculus, you wouldn't be able to understand that. So here's your integral. Maybe I'll zoom in with this thing. There. So these are the F3 keys. Let me go through that again. F3, second one is to integrate. I'm going to type in 1 divided by x, then do a comma. X is my variable of integration, comma, from 1 comma to 0.6 comma, or parenthesis. And there it is. Okay, I hope you guys can try that on your own, and I'll be happy to try to make another video if you have more questions about that. Okay, back to the computer. Example 2 says, use the properties of logarithms to approximate the indicated logarithms. Given that natural log of 2 is 0.6931 and natural log of 3 is 1.0986. So natural log of 0.25. Now 0.25 is 1/4, right? So that would be like saying natural log of 1 minus natural log of 4, which is natural log of 1 is 0 minus natural log of 2 squared. That's like negative 2 natural log of 2. I brought this 2 out front. The negatives from over here. That's negative 2 times 0.6931. And what do we get from that? Negative 1.3862. Natural log of 24 is next. Natural log of 24 would be the natural log of, I want to say 8 times 3. Why 8 times 3? Because then that's natural log of 2 cubed times 3. That's natural log of 2 cubed plus natural log of 3. That's 3 times the natural log of 2 plus natural log of 3. That's 3 times 0.6931 plus natural log of 3 is 1.0986. And what do we get from that? 3.1779. Next one is natural log of the cube root of 12. That would become 1/3 natural log of 12, which is 1/3 the natural log of 4 times 3. It's 1/3 times the natural log of 4 plus the natural log of 3. 1/3 natural log of times 2 times natural log of 2. Because natural log of 4, that's natural log of 2 squared. Plus the natural log of 3. So we're at 1/3 times 2 times 0.6931 plus 1.09, 86. That's going to give us 0.8283. And the last one like this is natural log of 1 over 72. That's natural log of 1 over 8 times 9. Think of this as natural log of 1 minus natural log of 8 times 9 because of the division. And of course, natural log of 1 is just 0. So we're looking at negative of natural log of 8 plus natural log of 9. Negative natural log of, let's distribute that through, natural log of 2 cubed minus natural log of 3 squared. That's negative 2 natural log of 2 minus, it's negative 3 natural log of 2 minus 2 natural log of 3. That's negative 3 times 0.6931 minus 2 times 1.0986. What do we get from that? negative 4.2767. Okay. Well, feel free to pause it if you need some more time on it. I'm going to move on. Example 3. Write the expression as a logarithm of a single quantity. We have 3 natural log of x plus 2 natural log of y minus 4 natural log of z. That's natural log of x cubed plus natural log of y squared minus natural log of z to the 4th power. Being a sum, this could be written as natural log of x cubed y squared minus natural log of z to the 4. Being a difference, we have a fraction, so it's natural log of x cubed y squared over z to the 4th power. Now E, we've talked about E before. You've seen it in your pre-calculus days. You may have even seen it if you took a discrete math class or a finite math class like Math 120, for example. So E denotes the positive real number such that natural log of E is the integral from 1 to E of 1 over t dt. And E is approximately 2.71828182846, and it goes on forever. It's like pi. It's irrational. It'll never repeat and never terminate. It has a lot of good uses, though. And then Calc 2, I encourage you to stick around for Calc 2 because we have yet another definition for E. You probably remember from your pre-calc days that there's a limit definition for E. I think it's a limit of 1 plus 1 over m to the m power as m goes to infinity. Okay, going on to page 3 here. Okay, theorem 5.3, derivative of the natural logarithmic function. Let u be a differentiable function of x. d dx of natural log of x is 1 over x. d dx of natural log of u is 1 over u du dx, or u prime over u. So this u's here, du dx is u prime. So differentiate the differentiation of a logarithmic function. d dx of natural log of 4x, this will follow this case here. It's going to be 1 over 4x times, what's the derivative of 4x? That's just going to be 4, which is going to be 4 over 4x, which just gives us 1 over x. d dx of natural log of x squared, that's going to be 1 over x squared times the derivative of x squared, that's 2x. So we have 2x over x squared. That's just going to be 2 over x. Okay, example 5 says find the derivative of the function y equals x, natural log of x. This is a product rule. So y prime is going to be x times the derivative with respect to x of natural log of x plus the derivative with respect to x of x times natural log of x. So y prime is going to be x times 1 over x plus 1 times natural log of x. Y prime would be 1 plus natural log of x. For example 6, it says find the derivative of the function natural log of x over x squared plus 1. So our function f of x could be written as natural log of x minus natural log of x squared plus 1. That's separating them out with the laws of logarithms. So f prime of x is going to be what? Well, the derivative of natural log is 1 over x. And now this derivative is going to be 1 over x squared plus 1 times the derivative of x squared plus 1 is 2x. So f prime of x is 1 over x minus 2x over x squared plus 1. Now if we want to combine into one term, we have 1 over x times x squared plus 1 over x squared plus 1 minus 2x over x squared plus 1 times x over x. So that's x squared plus 1 over x cubed plus x minus 2x squared over x cubed plus x. So in the numerator, x squared minus 2x squared is minus x squared plus 1 over x cubed plus x. Okay, feel free to pause that. I'm going to go on to page 4. Find the derivative of the function y equals negative square root of x squared plus 4 over 2x squared minus 1/4 natural log, of 2 plus the square root of x squared plus 4 over x. That is a messy problem. So I'm going to try to separate that if I can first. I'm going to move this up to give myself a little more space at the risk of going into the bright spot there. So y could be written as negative of x squared plus 4 to the 1/2 over 2x squared. So we're going to have a quotient rule here, minus 1/4 of natural log of 2 plus the square root of x squared plus 4 minus natural log of x. So y, I'm going to go one more step here. Negative of x squared plus 4 to the 1/2 over 2x squared, just brought that down, minus 1/4 the natural log of 2 plus the square root of x squared plus 4 plus 1/4 the natural log of x. Negative 1/4 times negative natural log of x is plus 1/4 natural log of x. So dy dx is going to be, do low d high, this negative here, negative of 2x squared times 1/2 times x squared plus 4 to the negative 1/2 times 2x minus, that's low d high minus high, which is negative, I got the negative out front already. So minus, what if I brought the negative? I could do that. I got the negative to this part here. I can do the negative there, and I don't have to worry about messing up my negatives. We're going to have x squared plus 4 to the 1/2 times 4x, that's the derivative from here, all over the square of what's below, 2x squared squared, minus, now this derivative is going to be, we have 1/4 times 1 over 2 plus the square root of x squared plus 4 times the derivative of this part. Well, that's going to be, the derivative of 2 is nothing, but the derivative of the square root part is going to be 1/2 times x squared plus 4 to the negative 1/2 times 2x plus 1 over 4 times 1 over x. Whew. So our dy dx is going to be, one of these 2's will cancel this 1/2. And we'll end up with negative 2x cubed over the square root of x squared plus 4 plus 4x times the square root of x squared plus 4 over 1. I do that because I can multiply it through now. Over 4x to the fourth. And this could be simplified a little bit. I could divide out the x, makes this a 3, and this here is a 2. I could divide on a 2. Okay, minus and the 1/4 and the 1/2. Oh, the 1/2 goes to the 2, so the 1/4 is still here. 1/4 times 2 plus the square root of x squared plus 4. On top, what do we have? We have 1 the square root of x squared plus 4 plus 1/4x. Now I'm only willing to go so far. I want to eliminate the complex fractions and I'll stop. So here I'm going to multiply by the square root of x squared plus 4 over 1. Down here, the square root of x squared plus 4 over 1. And same thing here, the square root of x squared plus 4 over 1. Square root of x squared plus 4 over 1. So that my dy dx is going to end up being, this would cancel here, negative 2x squared. You end up with a 2 times what's in here, those multiply out. So plus 2x squared plus 8. So these are going to go away, aren't they? And down below, you're going to have 2x cubed times the square root of x squared plus 4, and this 8 would reduce with this 2, leaves that as a 4. Then next we have what? That's going to cancel, leaves a 1 on top. Down below, it's really not nice down below, but it's not too bad. 4 times 2 times the square root of x squared plus 4 plus x squared plus 4 plus 1/4x. So if you clean it up a little bit, your final answer, the one I'm going to leave it with here, is going to be, that's 4 there, so 4 over x cubed times the square root of x squared plus 4 minus 1/4 times 2 times the square root of x squared plus 4 plus x squared plus 4 plus 1/4x. That was not too pretty. Okay, let's scroll down here and go to the next one. So pause if you want to pause that. This next one says use logarithmic differentiation to find dy dx. So as it sits, this is a pretty messy problem. You could do it. You got a product rule, you got a quotient rule going on, you got chain rules going on. It could be done though. I'm going to scroll this up to give me a little bit more board space to work. Now, natural log of y would be natural log of x squared times the square root of 3x minus 2 over x minus 1 squared. That would become the natural log of x squared plus the natural log of the square root of 3x minus 2 minus natural log of x minus 1 squared. And you can take that a step further, that the natural log of y would be, should we go there, 2 natural log of x plus 1/2 natural log of 3x minus 2 minus 2 natural log of quantity x minus 1. So if we take the derivative here, what do do we get? I'm going to come over here. That would be 1 over y times y prime. Y prime is our dy dx equals 2 over x plus 1 over 2 times 3x minus 2 times 3, that's the derivative of what's inside, minus 2 over x minus 1. Okay. That gives us 2 over x plus 3 over 6x minus 2 minus 2 over x minus 1. That's going to be 2 over x times 6x minus 4 over 6x minus 4. Yeah, I guess we have to do that. Times x minus 1 over x minus 1 plus our 3 over 6x minus 4 times x over x times x minus 1 over x minus 1 minus 2 over x minus 1 times 6x minus 4 over 6x minus 4 times x over x. So our 1 over y prime is going to become, we have the common denominator. If we start multiplying here, we end up with a 12x squared minus 20x plus 8 plus 3x squared minus 3x minus 12x squared plus 8x all over the common denominator, which is x times 6x minus 4 times x minus 1. Now, not much cleans up here, 12x squared, so that's about it. So from here we have 3x squared minus 15x plus 8 and that would factor to become 3x minus 2 times x minus 4 over, and if you factor this down, it's x times 2 times 3x minus 2 times x minus 1. So these divide out. So that 1 over y prime is x minus 4 over 2x times x minus 1. So if I multiply both sides by y prime would be x minus 4 over 2x times x minus 1 times, what was our y originally? It was x squared times the square root of 3x minus 2 over x minus 1 squared. So from here, the x squared and the x can go away, leaves an x up top. We have x minus 4 times x times the square root of 3x minus 2 over x minus 1 cubed. That is our dy dx. That's logarithmic differentiation. That's fun, huh? Okay, I'm going to go on to the next page, so pause if you want to pause. Okay, theorem 5.4, derivative involving absolute value. If u is a differentiable function of x such that u is not equal to 0, d dx of natural log of the absolute value of u is u prime over u. So find the derivative of the function natural log of absolute value of sine of x. And we have the absolute value because natural log, you cannot have a negative in there. The domain for your natural log has to be positive, and so the absolute value gives that to us. Okay, so our u in this case is sine x, so u prime is going to be cosine x. So y prime is going to be 1 over u prime, which is 1 over sine of x times cosine of x. That's cosine of x over sine x, which is cotangent x. So y prime is cotangent x. Okay, one more example from this section. Locate any relative extrema and inflection points. You use a graphing utility to confirm your results. Y equals x, x minus natural log of x. So y prime is going to be 1 minus 1 over x. So 1 minus 1 over x equals 0. Give us critical numbers. So 1 equals 1 over x means x equals 1. It's our only critical number. That's a relative extrema. Now if we take the second derivative, we have 0 minus negative 1 times 1 over x squared. So the power here is negative 1. So y double prime is going to be 1 over x squared, which is always positive, which means the whole function is concave up. So x equals 1 is a relative minimum. So y of 1 is going to be 1 minus natural log of 1, 1 minus 0, which is 1. So this graph looks something like this. Our min's at 1, 1. Okay, that'll do it for section 5.1. Hope you enjoyed it. Hope you're seeing this, you're growing with this, seeing how this is getting further and further, how we're learning more things we can carry with us. Okay, send me your questions. Thank you.